Swayam Prabha. Digital India. Educated India.
Welcome back. So let's continue the discussion on two-phase flows or combustion in two-phase media. So we started looking at the two-phase media and how a single droplet combustion can be estimated, where we can actually estimate the evaporation rate and time. So we will continue the discussion. So this is where we actually stopped. So this is what we got from the mass transfer based analysis, and the second one is the heat transfer based analysis. So for now the assumption here is that if the Lewis number is infinity, then we can write this balance, and then finally we can find out the fuel at the surface. So that A, small a, stands for the, this is at surface. Now how we estimate that? We can see this, T is assumed, the vapor pressure of the fuel is also determined using some table, then YF is evaluated from the equation, and we can check whether TS and YF satisfy this, otherwise we will go for iterator, and then finally we calculate BY and BQ using the initial condition of T infinity and YF infinity, and then we can estimate the evaporation rate, droplet, lifetime. So these are the two important parameters that we wanted to calculate. Now when you go to the single droplet combustion, there are also certain assumptions. So one is that the first assumption is that it is spherical burning droplet surrounded by spherical flame, which is means essentially we are assuming it's a, or simplifying to a 1D problem where m dot is in constant and function of radius. Now second one is that no interaction between droplets, that means it does not take into account droplet collision, and also sudden change in droplet size and number, partially premix combustion, therefore diameter only function of m dot and time. It is a quasi steady stationary in the gas phase, which clearly means that steady state in the gaseous phase, and we can use those assumptions. Then one component fuel, phase equilibrium at the surface, so which means no mixing inside, preferential diffusion to the droplet surface if one know the temperature, like Y underscore GA at F. Pressure is uniform and constant, which simplifies the analysis. Fuel oxidizer are products only, so that also is a simplification. Then fast chemistry, reaction at stoichiometric surface, which allows to use the conserved Keller's approach like mixture fraction concept, and then radiation is negligible, so which will also simplify the energy equation. Thermochemical properties are constant at Lewis number 0, no convection around the droplet, so that means all velocity is 0, and the size d0, temperature of the surroundings T infinity. So the whole idea is to calculate the evaporation rate, evaporation time, and flame position. The approach here is actually extends the development done for the spherically symmetric droplet evaporating in a quiescent environment, as we have discussed earlier. So we will retain the assumption of a quiescent environment and spherical symmetry in the initial development, but subsequently we can show how the spherically symmetric results can be adjusted to take into account the environment of burning caused by convection, either all these things. So that is essentially give you the this is how the inner region, this is the outer region from where oxidizer comes, this is fuel, temperature and the product, and this is the surface from where it goes. So this is the liquid zone, there is the inner zone which is between the outer zone. So we can write the mass conservation equation, and then the mass flow rate would be this, So, one can write fuel mass transfer equation in terms of fuel mass fraction YF, oxidizer mass fraction equation which is YOX, energy equation, and then we can use the stoichiometric. So, omega dot F will be omega dot oxygen by nu, delta C would be minus Q dot. Now, we also use the Fick's law of diffusion, so which is like this, and then we put it back in the equation system. So, what we get, m dot F equals to m dot double prime F YF minus rho d, where this is like this, and using this what we get, that rho s US and this, and here also finally rho s US, this is also US, rho d, and energy equation becomes, this is HFG, and if you look at the surface, this is the droplet surface through which the heat transfer comes in. So, it is a droplet temperature here is uniform. So, we write the fuel equation, oxidizer equation and energy equation, then multiply this one by delta AC and adding to this we get this, from where we can calculate BFT. Similarly, doing some algebra we can also get B oxygen T. So, this one can get, again going back to this. So, for the BF oxygen we can get. So, these are the calculations one can do, and so it just like fuel vapor multiply this, oxygen doing this, and then you do the algebra. So, you get this, where BFT you obtain like that. So, this is a simple algebra one can carry out and get it. And now, if the boundary condition, if we put R tends to infinity, B would be B infinity. So, this will give me this at the interface. Now, we integrate this, first integration constant, assuming rho d is this, then we can get, then substitute C1 in this equation, we get this one, and separation of variable give us this, and then finally after integration. Then the second boundary condition, R tends to infinity, B is B infinity, so we get C2, we put it back, this is what we get, and then finally this is what it is. So, these are the an evaporation rate m dot it 4 pi r square rho u r, this is how it is estimated. Now, the mass conservation or mass evaporation rate also estimated like this, and in order to determine the evaporation rate we calculate the Spalding number B infinity minus B s using this information and this. So, these are standard calculations, if you look at any textbook you can find this. So, more we can go into the what we observe here. The temperature of the flame did not appear in the burning rate directly. So, that is one of the observations that one can have. Secondly, the variation of B is not great among the different fuels, that is second thing. Then the burning rate being proportional to the ln1 plus B term will not change much as long as the oxidizing medium is kept the same. So, 10 times variation in B yields only 2 times variation in the burning rate, and the diffusivity and gas density dominate the burning rate. So, these are the observation which allows, and now this is a table which shows that the different transfer number for different fuel. So, this is the B or the Spalding number. So, temperature did not appear in the burning rate, variation of B is not great, burning rate being proportional to ln1 plus B term will not change much as the medium is the same, and the diffusivity and the gas density dominate the burning rate, and there is a 10 time variance in the diffusivity. So, that is what one get. Now, from the combustion system, B oxygen temperature is the most convenient form of B. So, one can write that it is a there is a change in Cp delta T, delta SC Yx by nu and HFG. This particular term is less than this term. So, basically the first term in the numerator is not that high compared to the second term. So, one can actually approximate this one like this. This is a fairly simple assumption and good enough assumption. Now, burning rate and the evaporation coefficient are readily evaluated, so it is not receipt. Now, here one can note the form of B oxygen T or BFT obtained in the analysis, assuming that the fuel droplet has infinite thermal conductivity, that is temperature inside the droplet is throughout that is maintained at Ts. So, that is one of the assumption. Now, at the interface if we do the heat balance, this is what coming out of the liquid, this is goes as a vapor, this goes in. So, if we write down the heat balance, this is what we get. Now, interface one write Q dot G M dot F HFG Q dot I to liquid. So, the negligible thermal inertia, simplest assume that the droplet rapidly heats up to temperature Ts, and there is a onion skin model which says that Q dot I to L M dot F CPL this. Here assumption is that the droplet as consisting of two zones, an inner region existing uniformly at its initial temperature T naught and the thin surface layer Ts. Then one can have transient heat up where it can be. So, droplet behaves as a lumped parameter, requires solving for energy and mass conservation equation for the droplet as a whole in order to obtain dTs by dt. Now, alternative approach is that one can estimate the B, and that would give a conservative results of the burning rate obtained by using this equation. Now, the estimation of the flame temperature and the flame radius Tf and Rf. So, we have R square Us by this already we have obtained. Now, using R square rho Vr which is constant equals to Rs square rho Vs, that means the essentially at the surface and the, so rho d is also constant. So, using this information in this equation we get this, and then we recall the Bf value, and that once we put. Now, at the flame location fuel and oxidizer would be 0. Using this the temperature of the flame and the Rf can be obtained. So, this boils down to this, and we use this equation. So, the ratio of Rf by Rs is ln 1 plus B by this. So, that is allow you the flame position Rf. Now, for the case of benzene, just an example, nu is this. Using this Pauling number 6, we can calculate this ratio to be 27. Now, for most of the fuel droplets burning in air, the flame standoff distance should be about 30 times the droplet radius. This value is much larger than which is observed experimentally due to assumption made with respect to the thermophysical properties and the Lewis number. That means the equal diffusivity, unit Lewis number. So, these are the assumption made these things to happen like that. Now, we have this. Now, again we starting from there. So, using this we can find out the flame temperature. So, Tf also obtained can be higher than the adiabatic flame temperature since the nitrogen diffused in this. And then the droplet lifetime, we have already seen the droplet lifetime and the radius can be obtained from the mass balance. So, dm by dt is minus m dot f, which is 4 pi lambda by this, and once we integrate we get this. So, this is the well known d2 law or d square law, and you can see for different fuels if you plot that how the it varies actually. So, the droplet lifetime can be easily obtained that Td is d square by k. So, that is the lifetime of the droplet. Now, we look at the heat and mass transfer balance. So, the heat conduction which takes place. So, this is our droplet radius, this is the flame sheet. So, in between this is the inner zone. Now, there is a heat transfer which comes in. Then the mass diffusion, analogous process to heat conduction using Fick's law, we can write this, that is the mass diffusion, and then this is the convection. This is applicable since at surface no fluid motion and energy transfer occurs only through conduction. Here the F stands for fluid. So, the energy transfer not only by diffusion, also by macroscopic motion of the fluid. If the difference in droplet and gas phase velocity exists, convection is mode of heat transfer. So, this would be heat flux would be Ht Ts minus, which is like that. And Ht is the convection heat transfer coefficient. Okay. And this is the thermal boundary layer and the temperature profile how, and the Ts is the surface temperature. Similarly, the convection of mass which is there, and there would be boundary layer thickness and the diffusion coefficient one can find out. Now, in boundary layer flows, constant heat transfer Ht can be expressed in terms of dimensionless variable like this. So, this come from the boundary layer equations where the non-dimensionalized is done and one can get those things. So, the non-dimensional number, the Nusselt number, which is at the boundary surface del T by del Y 0, or T star is function of this for given geometry, hence this derivative would be also function of like this, and the Nusselt number function of X star, Reynolds number and Prandtl number. So, the average Nusselt number can be obtained by integration over the surface of the body. Now, analogy. So, if you boundary layer flow, if you assume, then you can find out Hm, and then you can find out the Serud number and this. So, essentially it means that the convective heat transfer is only function of Nusselt number and Serud number for a given geometry. So, should be a similar for a variety of fluids. Length scale is not only dependent on this Reynolds number, Prandtl number, Smith number parameters. So, Nusselt number we can see it is a function of also, I mean by analogy we can see the Nusselt number would be also function of X REL, Serud number is also function of X REL AC, so like that. Now, we can see the effect of combustion here, the boundary layer type X. So, this is the surface, outer region, this is flame surface or flame length, this is how oxidizer varying, fuel varying, this is temperature and all these things. So, this you can see when there is a boundary layer, the profile actually changes, and that change takes place because of this boundary layer growth and all these things. Now, idea here move to heat and mass transfer boundary condition from film radius delta m for species and for energy. Film radius defines the concentration and temperature gradient, and heat and mass transfer rate are increased. So, the delta T by Rs is expressed as Nusselt number function, and the delta m is a function of Serud number. Now, if you have an convective environments where quiescent medium the Nusselt number equals to 2, and in general delta T by delta m equals to Prandtl number to the power 1/3. If Prandtl number is 1, then Serud number equals to Nusselt number. So, this would be estimated. So, there are different correlations which actually exist, and one can may look at that thing how. Now, again we can come back and look at the evaporation with convection. So, we have the R square rho UR dV by dr of this. Now, the boundary condition at the liquid gas interface, that is R equals to Rs. Now, we have rho S US equals to this. For integrating this one, we get C1, assuming the rho S ds this at Rs, we get this. Then when we get the C1, we will putting back, we get this, we separate the variable, and finally after integration we get the C2. Now, in the presence of convection, the energy equation, however, the boundary condition at the infinity are replaced by the boundary condition at delta T and delta M. So, we have already seen solving the energy equation, we can find out now due to the convection Now, instead of R tends to infinity, we use at the thermal boundary layer. So, oxygen profile at the mass boundary layer thickness would be oxygen infinity, delta T would be this. So, this one will get me back this once I put it this. So, the burning rate then results in m dot f equals to 2 pi lambda Rs Nusselt number by Cp. One can note here, this is not the only way to do these things. So, one can also do this by starting from the other equations or integrating the equation different equation, and then apply the boundary condition, can get this variable too. Now, we can see the effects. So, one of these the variable parameters. The gas phase thermophysical properties exhibit strong temperature and composition dependence. So, this is an important parameter and thermophysical properties which actually control this droplet combustion. Now, then there would be unsteady effect of fuel vapor accumulation. So, this is results in unrealistic large flame standoff distances predicted by D2 law. Droplet heating. Now, the evaporation rate depends on time varying temperature field within the droplet. So, we require more sophisticated model to capture that. Then it is a multi component fuel which is very important. So, if you look at these liquid fuels, they are not whether it is taking kerosene or ATF or diesel or something, they are really a multi component fuel. There would be aromatic ring, there would be other rings. So, the rate of evaporation of different component in a multi component fuel could be significantly different, which actually alter the fuel consumption rate. So, this is very important property, because in the practical system that we burn these fuels which are having actually multi component ingredients, and that changes the whole properties that we estimate from a single component fuel. Now, the interaction among multi component droplet is primary issue in spray combustion is the coupling of the variable ambient conditions to which the droplet is exposed during its lifetime. Then another very specific case which may occur in our space application or the semi cryo or cryogenic application, where it is a supercritical droplet combustion. Here the pressure is higher than the critical pressure. So, the latent heat of vaporization becomes 0 and the evaporation rate becomes infinity. So, that means as soon as the liquid comes out, it evaporates. Transient term in the energy equation is no longer negligible, as the gaseous mass in the region influenced by the droplet increases with pressure. Then the abrupt change of liquid phase to the gas phase and the droplet outer temp radius is replaced by the gradual density change. Then the radiation effect. So, radiation also increases overall heat transfer at the droplet surface, because some fuels when they burn, actually there is a lot of heat radiation effect. So, that can change those things. And then the internal circulation. In practically high pressure combustor, shear stresses of the liquid gas interface could be high enough to induce internal circulation within the liquid phase. So, these are the factors one can think about, then in realistic situation they can change the complete evaporation phenomena, their burning rate, consumption and all these things. It is not that simple. So, as you can see, as long as you are looking at the gas phase combustion and when you are coming here in the multi-phase combustion, things are quite different, because in the liquid phase there are so many other things that needs to be considered. Now, when you look at this internal recirculation, this is an Hill spherical vortex, this one is the Hill spherical vortex, and there is a different regions which are considered in Prakash and Srigano's model. So, this is the boundary layer region, this is the Hill spherical vortex, this is behind the vortex the wake region, this is axis of symmetry and all this. So, Prakash and Srigano, they developed a theoretical model. where this liquid phase, this is within the droplet. So, the liquid phase is divided in a thin boundary layer near the droplet surface in the liquid phase. So, this is what the thin boundary layer. Then the core region where the liquid motion was approximated by Hill spherical vortex, that means there is a region where the spherical vortex would be there, and the wake region near the axis of symmetry. Now, when you look at the system, the gas phase analysis or the motion near the surface analyzed by 3 different regions: stagnation point, boundary layer and the separation zone. And for boundary layer, Karman polarization integral approach can be used. So, this is quite important while determining the heat and mass transfer processes within the droplet, and that is why it also alter the evaporation rate. So, this is an important phenomena that takes place within the droplet. And there is another thing also within the droplet which actually happens is the flash boiling. So, that we will talk a little bit when you go to the actually the breakup and all these things, and we will see how that. Now, the application point of view, we have already seen this is a gas turbine application, industrial furnace, this is your liquid rocket, gasoline spray in the engine, spray dryer, diesel engine. So, these are all using a different kind of fuels which are actually multi-component. So, simplified analysis is good enough to give you some idea, but the realistic situation is quite different, as this multi-component system play an important role. Now, coming to then another important picture when this so far our discussion was on the single droplet combustion, their evaporation, looking at the surface. Now, whole point is that before we get the single component droplet or single droplet, it has to, because the liquid is injected like this or the fuel is injected like this as a form of through a injector. Now, that does not produce these single droplets. So, it goes through a process, and the process is first the fuel is injected. So, there could be exit flow, there could be cavitation, these are the things which may occur. Then primary, there would be a region where there is a primary backup takes place or the primary atomization. So, this is where the spray formation takes place, and then there would be, so there would be entrainment from the ambient, and then there could be a secondary breakup. That means from the primary the seeds break into smaller, the large side droplet, and then this will evaporate and makes rather the secondary breakup and the smaller size droplets are formed, and then it evaporates. So, that is why the vaporization is there. Once it evaporates, so it become in the gas phase. So, this is the gas phase where the fuel and air is mixed, and then once you ignite, the ignition takes place and the combustion goes on. So, from these to this there are, so you can see we talk about the single droplet combustion when from the gas phase to heat transfer and all these, which is actually in this position. But before that, the liquid which is also injected, that also goes through different stages, and that is why, and once it burns, you have a pollutant formation like NOx, particulate matter, unburned hydrocarbon, and you can look at this. So, the physical process occurs very simultaneously. So, dealing with all these complexities. So, that is why but in order to advance with current modeling capabilities, so it seems reasonable to aim for progress in individual sub areas, like one can look up the breakup, somebody can look up the dispersion, mixing and combustion, but which in other way cannot be viewed in complete isolation. Moreover, one has to consider the advantage and disadvantage of the different modeling approaches, like the DNS, LES and simulation based on RANS, probability density function kind of approach, and all these things. So, and also important is that you have a injection, primary iteration, secondary, then drop, collisions and all these things, dispersion. The important is that you have both Eulerian framework, you have both Lagrangian framework. So, the coupling between that two or completely handling in Lagrangian framework. So, these are the challenges that one has to look at it. So, we will see how these things are handled from the modeling perspective, and we will stop here today and continue the discussion in the next lecture.